Alright, so today we're diving deep into electric fields, a cornerstone of electromagnetism, and a concept that shifts how we understand electrical interactions. Rather than thinking about one charge directly exerting a force on another, we'll see how charges create fields that mediate these forces. By the end of this video, you'll have a solid grasp of electric fields, their equations, and how to apply them to real-world problems. Let's get started. Think of a charge as a spider and its electric field as a web. The field exists even if no other charge is nearby, but when another charge enters this field, it experiences a force, just like a fly getting caught in a spider's web. Electric field lines show us the direction a positive test charge would move. By convention, they point away from positive charges and toward negative charges. The strength of the electric field decreases with distance. It follows an inverse square law, meaning it weakens rapidly as you move away from the charge. These vectors help us visualize both the direction and magnitude of the field at different points. Which way do the field lines point for a positive source charge? A, toward the charge, B, away from the charge, C, in circles around the charge. Take a moment to think about it. The correct answer is B. Field lines always point away from positive charges. Let's define the electric field mathematically. The field strength E, created by a point charge Q at a distance r, is given by E is equal to kq over r squared, where k is Coulomb's constant 8.99 times 10 raised to power of 9. This equation tells us that the field depends on the charge Q and the distance r. Let's calculate the field strength 5 centimeters from a plus 3 nanocoulomb charge using this formula. Solving this gives E is equal to 1.08 times 10 raised to power of 4 Newton per Coulomb. Since the charge is positive, the field points away from it. When a charge Q enters an electric field, it experiences a force given by F is equal to QE. This equation connects the electric field to the force experienced by a charge. If Q is negative, the force direction is opposite to the field. A negative charge Q equal to minus 2 nanocoulomb placed in a 1.08 times 10 raised to power of 4 Newton per Coulomb field. The force is minus 2.16 times 10 raised to the power of minus 5 Newton. The negative sign indicates that the force is opposite to the field direction. If a plus 1 nanocoulomb charge is placed in this uniform field of 500 Newton per Coulomb, what is the force on the charge? Pause here to calculate. The answer is B. Electric field strength is visualized through line density. Denser field lines indicate stronger fields, while more spread out lines show weaker fields. Remember, the field strength decreases as 1 over r squared. If the field at 2 meter is 100, then at 4 meter, the field is 25 Newton per Coulomb. Doubling the distance reduces the field strength by a factor of 4. A uniform electric field has parallel field lines and constant strength everywhere. This occurs between two large charged plates. Lightning occurs because of strong electric fields between clouds and the ground. What do you think the field lines would look like? Picture it before we reveal. To recap, electric fields represent the influence of charges on space. The field strength depends on Q and R. Fields determine the force on a charge, calculated as F is equal to QE. Test your understanding further with King of the Curve. Visit kotc.me for practice questions, interactive tools, and resources to master physics concepts. Thanks for watching, and see you next time.